Yeah, so welcome, Vincent. Very glad to have you here. So just a brief introduction. Vincent just finished his PhD at Stanford with a thesis on self-supervised scene representation learning, a lot of topics that are very close to our research interest here in Tübingen as well. And so we're very glad to have you here. And he is moving to Josh Tenenbaum's group at MIT soon, or has already moved recently. Thanks for coming, and we're looking very much forward to your talk.
Thanks so much for the introduction and for having me. I'm really excited. Your work has been, you guys' work has been a huge inspiration, as you're going to see momentarily. Yeah, so I'm going to talk about implicit neural scene representations, and let's just jump right in. So many of us in the Zoom call and in machine learning more generally, we are interested in building models that take as input some kind of signal, and then from that signal learn something about our world. In computer vision, for instance, our signals are images, and we build models that look at an image and then learn something about our 3D world. So now the first point I want to make is that the way we choose to represent a signal has a huge impact on the kinds of models we build to analyze the signal afterwards. And it is worthwhile asking, how do we represent our signals today? And most of the time, we represent signals discretely. So for instance, images are discrete grids of pixels. Shapes are usually voxel grids or point clouds or meshes. And audio signals usually are discrete grids of amplitudes. So the first point I want to make is that imagine we hadn't chosen to parameterize images as grids of pixels. Would we still be using convolutional neural networks today? And convolutional neural networks arguably are like rule computer vision these days. But just imagine we had instead parameterized images in some other weird way that we don't know about. Would we have chosen to like discretize them into grids of pixels and then like process them with convolutional neural networks? I don't know. And I think that's a very interesting and intriguing question, because seeing how much this choice of parameterization has impacted the algorithm, it is very worthwhile to think about if we had a different parameterization, would we come up with different algorithms? Because to me, it's not at all obvious that this is a particularly good or a particularly bad parameterization, and maybe there are other better ones. And as you all probably know, recently there has been a new kind of representation proposed for 3D shapes, also from this group here. And the key idea here is to encode a 3D shape in the weights of a neural network. And particularly, we represent a shape, a 3D shape, as a neural network that maps an XYZ coordinate to either the occupancy of the 3D shape at that XYZ coordinate or the signed distance of the shape at that XYZ coordinate. And why does that make any sense? It has a few key benefits. First of all, this parameterization is agnostic to the resolution of some sampling criterion that we think up. The complexity and the memory that the model requires scales with the complexity of the signal and not with, again, the sampling density. And this admits the learning of priors much more effectively than conventional shape representations. And that has enabled super cool results in the occupancy networks paper, for instance, with few shot reconstruction of 3D shapes. So this is a very interesting kind of parameterization, and I refer to these representations as implicit neural representations. And it is worthwhile asking, in all of these papers, these parameterizations have been used to parameterize these simple shapes, like this little Stanford bunny here. Can we also use these to parameterize more complex signals and more complex shapes? And if we go, for instance, to a room scale scene from the ICL-NUM dataset, like this room here, and we use the ReLU MLP that was proposed concurrently in these papers, we'll find that it doesn't actually work. The ReLU MLP cannot manage to capture all the fine detail and all the geometry in the scene. And moreover, you can ask, do these implicit neural representations in principle also work for other complex signals, such as, let's say, images, or for audio signals? And unfortunately, you'd find that these ReLU MLPs cannot easily parameterize signals such as images or audio. And what's more, the language of physics in our world are partial differential equations. many, many natural signals are defined as the solution to a partial differential equation, such as like audio waves or light waves. But it turns out that if you try to parameterize such signals with a ReLU MLP, for instance, that also does not work. And so that's a big problem, because we might want to model physics in our world with these kinds of implicit neural representations. So the first question you might ask yourself is like, why is that? Why does that not work? And there's lots of unanswered questions here. So this is still an area of active research, but there's already a few things we know and that are also very intuitive. So we're going to talk about these now, and we're going to look at a ReLU MLP. The first insight you can arrive at is that the functions that are learned by implicit neural representations with conventional nonlinearities are not generally shift invariant. It's very hard for a ReLU MLP to learn to apply the same function at two different XYZ coordinates. And that is a problem if you want to parameterize signals that have information spread out over a large domain and that have very fine detail information across the whole domain, such as an image, for instance. Another problem is that when it comes to physical signals, it turns out that these conventional architectures fail to parameterize the derivatives of signals as well. And for ReLU MLPs, this is kind of intuitive and can be seen quite easily, because any function you parameterize with the ReLU MLP is piecewise linear, which means that the first derivative is piecewise constant, the second derivative is is zero everywhere. And that immediately means that you cannot parameterize any signal that carries any kind of information in the second derivative with a ReLU MLP. For instance, solutions to the wave equation or to the Helmholtz equation. For other kinds of nonlinearities, it's not obvious why this would be the case there as well, but we'll see that other nonlinearities, like tanh nonlinearities, similarly do not do a great job at parameterizing the derivatives of signals. So how can we fix this? How can we fix it? And this is our most recent work, and we call them sinusoidal representation networks. And it's a very simple multi-layer perceptron architecture. And the key idea is we replace conventional nonlinearities such as the tanh or the ReLU nonlinearity with the periodic sign. And we have an initialization scheme to go with it. So of course, we can do that. We can use as an activation function whatever we want. Why does this make sense? The first thing that you can convince yourself of is that you gain a degree of shift invariance by doing this. And you can see this by just looking at the first layer of the siren network. If the first layer generates the same set of activations for two different input coordinates, then necessarily the rest of the MLP will apply the same function at these two different coordinates. Now, if you look at the very simple case of only having a single neuron in the first layer, and it has a sign activation, then you can convince yourself quite easily that because the sign is periodic, it's going to generate the same embedding for lots of its input domain, or for many points along its input domain. And that gains you a degree of shift invariance. And so you can convince yourself that for this architecture, it's much easier to learn to apply the same function at several different XYZ coordinates. And now when it comes to derivatives and parameterizing solutions to partial differential equations, the sign also has a very, very special property. Namely, the derivative of the sign is the periodic sign itself. It's, or like the cosine, it's just a shifted sign. And indeed, you can show that if you take the derivative of the output of this MLP with respect to its input coordinates, the neural network that you get that parameterizes the derivative is again a neural network that you can express as an MLP with sign nonlinearities. And so you can argue that the derivatives of this network inherit some of the properties of the network itself. And so now you can go ahead and you can try out to parameterize all these different signals with this new kind of architecture. And you'd find that indeed, this architecture can parameterize all these signals and do so quite well. And in the paper, we try this for a variety of signals. We're only going to talk about 3 today that are representative for our work. And first, we're going to talk about audio signals. So audio signals are potentially the easiest ones because there's no derivatives involved. This is really only about parameterizing the signal itself and doing a good job at capturing the signal. And what is our training data? Our training data is the discrete audio signal, which means it's tuples of time points plus amplitudes. And now what we want to do is we want to fit an implicit neural representation directly to this data set. So it's just an L2, the loss is just an L2 loss on this tuple of time points and amplitudes. Okay, and like now I'm going to play the audio. I hope you can hear it. So this is a sample from Bach's sonata, I believe. So now, if you go ahead and try to parameterize this audio signal with a ReLU MLP with K-MK initialization, then this is what you get. So not quite there. Now, if we do this with a ReLU with a positional encoding, as proposed by Mildenhall et al. In 2020, we can already do much better, but it's still very far. And now, here's what you can get with siren parameterization. So evidently, the siren manages quite well to parameterize and to capture the detail in the signal. And so we also show this for images and video signals, in which cases you just map XY pixel coordinate or XYT pixel coordinates to color, and it works similarly well. But now we're going to make it a little bit different and a little bit more difficult. Let's say we want to parameterize an image with a implicit neural representation with the siren, but we don't actually have access to the image values, like the grayscale values at each pixel itself. All we have access to is we have access to the gradient of the image at each XY coordinate. And we want to reconstruct the image in the primal domain, so to speak. So now, you can show that this is equivalent to solving Poisson's equation. And the key idea, what we're going to do here is, instead of supervising the output of the siren directly, the output of the implicit representation directly, we're going to supervise the derivative of the siren with the gradient. So now our data set are XY pixel coordinates, and at each XY pixel coordinate, we have access to the gradient. And we're going to compare the convergence of a few different MLP architectures with all the same parameter count and so on. And here on the right, in the right column, you can see that will be the output of siren. Then there's the 10H nonlinearity. Then there's the ReLU position encoding from Mildenhall et al. In 2020, and then there's the soft plus. And on the left-hand side, we have ground truth. The top row, that's the image. And the image we do not supervise. So none of these architectures ever actually have access to the ground truth pixel values. Then in the second row, that's the gradient. That's the thing that we'll actually supervise. And in the third row, that's the Laplacian of the image, which we also do not supervise. We just visualize it for visualization purposes. Okay, so now we're going to see how all these different architectures fare in solving Poisson's equation. So now we are approximately 100 iterations in, and you can see that siren has already fit the signal quite well. And you can see that even after 4,000 iterations, siren is still the only architecture that fits the gradient particularly well, that has any kind of high frequency information in the gradient at all. It's the only parameterization that has any high frequency in the Laplacian as well. And it has achieved a much higher PSNR in the image domain as well. So evidently, siren manages quite well to not only parameterize the gradient, but it also allows us to supervise derivatives of the network architecture and retrieve the signal itself. And you can make the same experiment with the Laplacian with exactly the same result. Cool. So now we come to the Acknowledgement equation, which is closest to the initial idea of implicit neural representations. And what we're trying to do here is we're trying to find the sign distance function of a complex scene. And we're going to pick this room from the ICL NUM dataset as an example. But the setup is a little bit different. We're not actually going to have access to either the ground truth occupancy at every coordinate or the ground truth side distance at every coordinate. Instead, all we'll have access to is a oriented point cloud, which means we'll have access to surface points. Our data set is going to be a point cloud of surface points. And at every surface point, we're going to have access to the surface normal at that surface point. And I'm going to briefly walk you through the loss because every term in this loss function tells you something about the Acknowledgement equation about sign distance functions, which is quite cool. So in the first row, we have this integral over the with this omega 0, by which we mean all the surface points. And first, we penalize the output of the implicit function phi itself on all surface points. And that's intuitive because for a side distance function, the side distance function is 0 on all surface points. That's the first loss term. The second loss term, that's the 1 minus the inner product of the gradient of phi and the gradient of the surface normals. Gradient of fx, that's the surface normals. And this means that on the surface, the gradient of the side distance function has to align with the surface normal. And this is a property of side distance functions in general. And now the second line is interesting because that's what makes it a particular Acknowledgements equation. Now we are integrating, we're looking at all the points in space, so not only the surface points. And we're saying that for all the points that we sample, the norm of the gradient has to be 1. And that's basically what makes this a side distance function. The reason being, if you are at any point in space, if you walk from that point of space to the closest scene surface and you integrate along the integrate the gradient along that path, it has to integrate to this to the distance. That's why the gradient norm has to be 1. Cool. So so what we're effectively doing here is we're solving a partial differential equation to retrieve the side distance function. And we're going to compare a ReLU MLP with Siren again. And both in the video and in the paper, we say that this is an MLP with 5 layers and 1024 hidden units. Actually, we got that wrong. We checked the code again. It's actually only 512 hidden units. So this is 5 layers, 512 hidden units. It's a single fully connected neural network. And on the right-hand side, you have Siren. On the left-hand side, you have the ReLU MLP. And what you can see is that the ReLU MLP does not manage to capture the fine detail in the scene at all. The curtains are maybe the most obvious part, but the walls aren't smooth. It misses the legs of the sofas. And in general, the reconstruction is just not particularly good. But Siren manages to faithfully capture the geometry of this large scale scene in extremely few parameters. Cool. So now we have shown for a bunch of signals that we can parameterize these signals, even if the definitions of these signals involve the derivatives. Of course, in the long run, where we want to get is we want to learn priors over the space of implicit functions. And we have a proof of concept of that. So there's definitely more work to be done here. But what we did in the paper is we wanted to learn a prior over the CELAB A32 by 32 dataset. So as in the conditional neural processes paper from Garnello et al. So we have a set of pixel observations. We have an encoder that takes these pixel observations and produces a latent code. And then we have a fully connected hypernetwork that takes this latent code and translates it into the parameters of the respective Siren representation of that image. And at test time, what this allows you to do is it allows you to do image reconstruction from varying numbers of pixel observations. So here in the top row, you can always see the samples, pixel samples that are the input to the model. And in the row below, you can see the sampled Siren. And you can see that indeed, this architecture manages to learn a prior over these spaces. And of course, there's more work to be done in terms of fidelity, but clearly this architecture does allow you to learn a prior over the space of functions that parameterize these CELAB A images. Awesome. So the title of this talk is Neural Scene Representations. We haven't talked about scenes much, though. We have talked a little bit about scenes, which are
Can I quickly ask a question maybe in between?
But in a way, we cheated a little bit because we supervised these representations in 3D with the ground truth point clouds. So we had access to 3D information. Oftentimes, however, we do not have access to 3D information. Let's build a little toy example here. Let's say our data set were ShapeNet cars. So our scenes now, each scene is just a single ShapeNet car. And of course, these ShapeNet cars are 3D objects. They're 3D scenes with color and geometry. But regularly, the observations we have aren't 3D. The observations we have of 3D scenes are often just images. So they are 2D projections of this 3D scene. But from these 2D observations, we want to reconstruct the underlying 3D scenes. And so this is different from all the things we've looked at so far. And of course, we want to do this with implicit neural representations again. But how do we go about that? The nice thing about this is if we manage to do this and if we manage to solve this problem, we would be much happier for it, because of course we have access to a lot of 2D data. 2D data is very cheap to collect, and you could just go on YouTube. There's billions of hours of people running around with cameras. So that would be awesome. So in any case, let's just set this in stone. We want to train on 2D images. And we're going to build a little framework that allows us to experiment with different kinds of representations, training in this framework. So we will always have some kind of algorithm that goes from a set of 2D observations to a neural scene representation. And that's the representation of the underlying 3D scene. Now, because our observations are in 2D, we need to find a way to go from that neural scene representation to our observations again. And that's going to be a neural renderer. So we're going to build a differential renderer that allows us to go from the scene representation to a set of 2D images again. And that will allow us to close the loop and render out the same observations that we have in the training set, and then supervise the whole thing end to end with an image loss and train everything end to end. Okay, so yeah, this is what my thesis was about. So I refer to this framework as self-supervised scene representation learning. It's self-supervised because we are training it with observations that you can just collect with a camera, so images, and scene representation learning because in the end, what I care about is really the neural scene representation. Like in the end, we want to learn rich representations of 3D environments that we can use for a variety of different applications. So in the short history of modern machine learning, so in the past, let's say 10 years, I guess, many people have looked at this problem, and maybe it is worth asking what is like the simplest incarnation of a model in this framework. And maybe the simplest incarnation is a slight variation of the 2D convolutional autoencoder. And this was proposed by Tatatenko et al. In 2015, so quite ahead of its time. So the key idea here is you have an image observation, you have a convolutional encoder that gives you a latent code, encodes the image into a latent code. You concatenate that latent code with the pose you want to render and decode that into an image again. And then you can train the whole thing end to end. So in this framework, the encoder is the algorithm that goes to the neural scene representation, the latent code, that's the neural scene representation, and the renderer, that's the decoder plus the output pose. Now, if you go ahead and you train that on ShapeNet cars, so 2,500 cars, 50 observations each, and then you try it on cars in the test set, this is what you get. It's actually, it's pretty cool that this does anything at all, but it clearly doesn't manage to capture the 3D geometry and appearance of these objects accurately at all. And in fact, you wouldn't expect it to either, because you haven't actually told the model in any way or constrained the model in any way to find an explanation of the training data that respects multi-view and projective geometry. So the model has found probably a perfectly fine explanation of the training data, just it has done so without 3D, and it has cheated. So what we need here is we need an assumption. We need to make an assumption that this data lives in 3D, such that our model finds the solution we're looking for. So we need a 3D inductive bias. And at the time when we started thinking about this, there were a few kinds of, directions of related work. And we're going to look at these in terms of whether they have 3D structure or if they can be trained self-supervised just with images. So there was this line of work, scene representation learning, such as neural scene representations and rendering from DeepMind. And these models can also be trained just with images, but they do not have any 3D inductive bias, which makes them extremely data hungry, and they don't work on small data sets. Then there's 2D generative models, and the same thing applies. They can be trained just with images, but they don't have any kind of 3D structure, and so they cannot discover 3D geometry and appearance by themselves. And then there's 3D computer vision, and this one is interesting because in 3D computer vision, it has been proposed for a long time to use either voxel grids or point clouds or meshes as the output of the model. And this is a very clear 3D inductive bias. You tell the model your predictions have to lie in 3D in the end. But these usually can't be just supervised with images. And on top of that, they are only concerned with geometry. But we want to parameterize maybe all aspects of scenes. So now, this is 2018 when we came up with deep voxels. And the key, and I'm just going to briefly talk about deep voxels because it's not an implicit neural representation, but it was, for us, the first model that fell into this framework. And the point of this project really was to investigate whether this 3D inductive bias buys you anything. So if you have a 3D structured representation, does that buy you anything? Do you do any better? So this model didn't generalize across scenes at all. The key idea here was we want to find a neural scene representation for just a single scene. So we have a lot of observations. We have some kind of optimization algorithm that I'm not going to talk about, arrives you at a voxel grid of features. And that's now how you represent your scene. So it's a 3D voxel grid of features. And then we implemented Mule Renderer that basically allowed you to render this voxel grid from arbitrary camera perspectives using multi-view and projective image formation. And indeed, we showed that that works much better than models without a 3D inductive bias. So here's a quick baseline comparison. On the bottom right corner, that's the output of deep voxels. Top left is ground truth. And then you have 3 architectures that don't have a 3D inductive bias. And you can tell that these models cannot render novel views of this object particularly well, while deep voxels can. And that also worked on real data. So here you can always see on the right-hand side, the nearest neighbor in the training set, and on the left-hand side, the output of deep voxels. And you can see that deep voxels manages to generate quite high quality results. So if that works, like, why aren't we done? Why can't we just leave it at that? Well, there's a few limitations here still. Voxel grids are very memory inefficient. They scale cubically. The memory they require scales cubically with the spatial resolution of the scene. They do not parameterize scene surfaces smoothly. And that's more of a kind of an elegance argument. But if you have a white wall, you don't want to discretize the white wall and then like store the information that this is a white wall in every voxel. Maybe you want some kind of more compact representation. And it turns out that generalization with voxel grids is very hard. So I am still unaware of a paper or of a project that can go from a single observation to a high quality reconstruction of a voxel grid. It's very hard to learn priors over these voxel grids. Okay, so now, of course, we already know the solution. The solution is going to be an implicit neural representation. So let's think about that for a moment. If we were to represent scenes via implicit neural representations, how would that look like? And we're going to take a step back and just think about a very simple scene for starters. So the gray background here, that's free space. Then we have 3 objects, a green circle, a red square, and a blue triangle. And we have a coordinate frame that's the 2 x-axes. So now what we proposed is to model a scene as a function that maps an XYZ coordinate to a feature representation of whatever is at that XYZ coordinate. And that's a little bit different than the things we looked at with sirens before, because when we parameterized all these other signals, we always knew what the thing is that we want to map to. It was maybe for images, it was a color. For audio, it was an amplitude, and so on. But now for 3D scenes, we don't. Like, if we want to parameterize all aspects of a scene, we want to have a feature that could encode all kinds of information. It has to encode information about geometry, appearance, potentially lighting, surface properties, and so on. So let's just say on an abstract level, a scene is a function that maps an XYZ coordinate to a feature representation of whatever is at that XYZ coordinate. So in that framework, what does a voxel grid do? A voxel grid discretizes this function and then performs a lookup. And we already discussed why this potentially has downsides. So now in scene representation networks, we proposed to parameterize the scene directly as a fully connected neural network that learns to map XYZ coordinates to feature representations at these XYZ coordinates. And if we think for a moment, how does this then parameterize scene geometry, and how does this parameterize the scene then? And we looked at this little like corner of this red square, and we realized that geometry, similar to occupancy networks and sign distance functions, is now again represented implicitly. So the geometry is now only defined by this level set of this neural network. But now basically there's a feature inside the red square that says I'm a red square, and then there's a feature outside the square which says I'm free space, and the geometry of the square is defined as the 2D subspace where basically this feature changes. However, if you manage to do this, this again has the same upsides as implicit neural representations in general. It will be, you can sample it anywhere and at arbitrary resolutions. It parameterizes scene surfaces smoothly, and the memory it requires scales with the complexity of the scene. Okay, so that's the scene representation. Now, what does the neural renderer look like? And we're going to look at our simple scene again, and we're going to place a camera now, and we want to render the scene from this camera perspective. The first problem we'll have to solve is we're going to have to find the intersection of each camera array with scene geometry. And why is that? That's because now we don't have any explicit parameterization of scene geometry anymore. So now we have to find the surfaces first. And we're going to do that with ray marching. So we're going to start close to the camera, march along the ray until we hit the surface, and then we proceed from there. And we could just pick, for instance, a constant step length, and then step along the ray and define a criterion on when to stop. But that has the downside that it takes a very long time, and we will have to backpropagate through that. So that's not ideal. So can we do better? We can. Let's look at the single camera array here. And we're going to start close to the camera at this coordinate x0. The first thing we're going to do is we're going to sample our scene representation at this coordinate x0, and we're going to get a feature vector which describes local scene properties. And now what we're going to do is we're going to translate that feature vector into a step length, and we're going to advance along the ray according to that step length. So now, of course, we can do that, but why does this make any sense? Is this just like deep learning magic, or is there something going on here? And there is. So fundamentally, this is identical to asking the question, does there exist a function that maps every xyz coordinate to a feasible step length? And we already know one such function. That would be, for instance, the constant one. So we could map every xyz coordinate to like a small constant step length, and that would be fine. But another one is the sign distance function, which we interacted with before. And that maps every coordinate to the distance to the closest surface. And that's, in this case, the radius of the circle here, which just touches the surface of the red square. In this case, this algorithm is called sphere tracing, and it was proposed in the 80s, I think, for ray marching analytical sign distance functions. And you can convince yourself that the sign distance function indeed is a feasible function to ray march your sign distance function. This implicit neural representation. And because you're going to take steps, and as you get closer to the surface, you will take smaller and smaller steps until eventually you'll arrive at the surface. And you're guaranteed never to step through the surface. So now what we're doing here is we aren't exactly ray marching the sign distance function. Instead, we implement a ray marching long short-term memory, which has a memory as it steps along the ray, which allows it to take larger step sizes, for instance, and reason about the sign distance function as it goes along the ray. But the basic idea is the sphere tracing algorithm. Now we're going to iterate this for a fixed number of iterations. And we call the last iterate our intersection with scene geometry. And now we need to render a color for each ray. How are we going to do that? We're going to sample our scene representation the final time, gives us a feature vector. And now we're going to translate that feature vector into the color at that coordinate. Cool, so now we have the whole end-to-end pipeline together. So now we can train this thing on a single scene, great. However, what we still haven't discussed is how can we now generalize across scenes, and how can we learn a prior across a class of scenes? Let's think about that. So let's say we represent each scene in our data set with its scene representation network. Then you can say that the parameters of the network, this is the parameters of the scene representation of the scene itself. This is a very, very high dimensional parameterizations in the 100s of thousands of parameters. Probably don't need that, so we do the thing that we often do in machine learning. We'll represent each of the scenes with a low dimensional embedding vector. And now we're going to take the embedding vector and translate it to the parameters of the scene representation, again with a hypernetwork. It's just a fully connected neural network that takes an embedding vector and produces the parameters of the scene representation network. And now this is the thing that can learn priors over scene representations. This can learn cars have four wheels. They're like, this approximately this in the shape. They're usually symmetric and so on. Cool. So that's how we're going to learn priors. And that will allow us now to do few shot reconstruction. So how are we going to test this? We're going to train our model on ShapeNet cars or ShapeNet chairs, 50 observations per object. But at test time, we'll only give our model a single observation of an unseen car or chair. And you can see the input post on the lower left-hand corner. So it's this 3/4 view. And here's the renderings of novel unseen camera perspectives. In the top row, that's scene representation networks. And then in the rows below, that's, again, architectures without a 3D inductive bias. And you can see that scene representation networks manages to render almost perfectly multi-view consistent. And what isn't shown here is that scene representation networks also gives you an unsupervised reconstruction of scene geometry, because for each camera ray that you ray marched, you have the length of that camera ray. So you get the depth map and the normal map for free. And you can see that here. So these are all, oh, the video doesn't play. Let's try that again. There we go. So these are all cars and chairs in the test set, and you can see that it works quite well. And of course, there's failure cases. For instance, on the top right-hand corner, you can see that this chair, the legs were, it failed to reconstruct the legs. The cool thing, though, is that you can always look at the geometry. And in this case, you can see that it tried to basically explain the chair as an office chair with like the spinning contraption at the bottom. And now at least that gives you insight as to how this failed. Of course, no solution yet. So that is still work to be done. So now we can just go through a few properties. You can sample it at arbitrary resolutions. So we trained this at 128 by 128. At test time, you can just shoot rays more densely and render the whole thing at a high resolution. Something that I'm extremely excited about is this capability of generalizing to completely unseen camera perspectives. So this model here was trained on ShapeNet cars, but it has never seen a car up close, neither has it ever seen a car on its head. But because we have this assumption that the data lives in 3D, we have this 3D inductive bias, this model generalizes to these completely unseen camera perspectives just fine. And of course, if you try this with a convolutional neural network, like the AutoDecoder that we talked about, you'll find that it just doesn't do anything at all. It's like there's no support for these camera poses in the training set, so it won't be able to generate them. If you interpolate the latent codes for chairs, for instance, that is equivalent to interpolating both the geometry and the appearance of these objects. And you can see that from object to object, the features of each object transform into each other quite smoothly. And if you already had a disentangled latent space, let's say you had a latent space where you knew that each latent code mapped to a face with a different facial expression, but the same face, then if you interpolate it between these latent codes, it's like kind of a poor man's animation. So the reason why I like this example again is because it doesn't only shift around the pixels on the face on the right-hand side, but you can also see that the model actually modifies the geometry of the underlying face. And lastly, you can raise the question, does this now also work for more complex scenes? So the order of this talk notwithstanding, this was actually a project we did before Siren. So this is still with value MLPs, including their limitations. But nevertheless, here we show that you can indeed also represent more complex scenes, such as this still arguably pretty simple room from the GQN dataset. And I placed 2 ShapeNet cars in this room. However, these scene representation networks right now are compositional. So if you train them on rooms with 2 ShapeNet cars and you try to reconstruct a room with 4 ShapeNet cars, that's not going to work. Cool. I want to briefly bring up related 3D scene representations. So there was PyFu, which I'm a huge fan of. So PyFu allows you to reconstruct humans from only a single observation at test time as well. However, and it generalizes across scenes, therefore, that's why it allows you to do that from only a single observation, but you can't train it without ground truth shape because there is no differential renderer in the loop. So you require at training time ground truth shape for each of your training examples. And then, of course, there's voxel-based representations, and I just want to contextualize this again because the interesting thing here is that these voxel-based representations allow you to do much more complex scenes as of now, and much more high-quality reconstructions. Similar to the recently proposed NERF, and allow you to do null view synthesis that is almost photorealistic. But neither of these architectures allow you to generalize across scenes. So you always require lots and lots of observations to fit a scene. And to me, this is one of the most interesting conundrums in this line of research right now. You can either have generalization, but then you are constrained to these pretty simple scenes. Or you can have photorealism, but then you always need densely sampled observations. So maybe we can tackle that in the next few years or months, who knows. Awesome. So now I kind of glanced over how exactly we train these hypernetworks, but now we're going to get back to that. So let's actually walk through a forward pass of how a single training step works with these hypernetworks. And then we're going to discuss a problem with this training procedure for generalization. Okay, so the way we train these hypernetworks is in the so-called AutoDecoder framework that was also used in the deep SDF paper. What that means is that at training time, each of the scenes in your data set gets a latent code, and that latent code is randomly initialized. And these latent codes are free variables. So now, how does a forward pass look? You pick an observation from your training set. You retrieve the respective latent code, and you map that latent code to the weights of the respective scene representation with the hypernetwork. Now we render the same camera pose as the observation that we picked. We enforce a re-rendering loss, and now we can backpropagate that loss. What do we backpropagate it into? We backpropagate it into both the weights of the hypernetwork and the parameters of the latent code. Okay, so you can train this thing at training time, works great. How do we do test time reconstruction? At test time, you need to randomly initialize a new latent code. Then we're going to map that randomly initialized latent code to, at the beginning, basically random scene representation. We're going to render out the observation that we have of this car. So for instance, let's say we only have a single observation, as in the single shot reconstruction case. We can enforce our re-rendering loss again, but now we're not going to backpropagate it into the weights of the hypernetwork anymore. We're only going to backpropagate it into the latent code itself. And this is equivalent to basically asking, given this prior that we learned, which is the weights of the hypernetwork, that's our prior, what is the latent code that best explains this observation? And then that allows you to do few shot reconstruction. The problem with that is that it takes on the order of seconds to minutes to do test time inference with this. So for instance, deep SDF, I think reconstructing a single airplane takes like 8 seconds. For scene representation networks, if you until it's fully converged, takes about 2 minutes per object. So this is not acceptable at all. So this is a new project we did recently as well. And this project is called Meta SDF, and it's with Noah Snavely and Richard Tucker and Eric Ryan-Chan. And the key idea here is that now we are going to leverage gradient-based meta-learning to generalize across a space of implicit neural representations. We're going to look at signed distance functions because they're a little bit easier than scene representation networks. And so the key assumption is that imagine you had a neural network that parameterized each, let's say, airplane in your data set of airplanes in ShapeNet. We're now going to assume that all these neural networks are specializations of an underlying meta signed distance function. And we're going to ask that this meta signed distance function allows you to retrieve any of these specialized neural networks in very few gradient descent steps. So we're basically asking, can we find a neural network architecture that allows us to quickly specialize to each of these signed distance functions in very few gradient descent steps? To make that a little bit more clear, we'll walk through a forward pass again. So the free parameters that we have are the parameters exactly of this meta signed distance function. So it's just a fully connected value neural network again. So now at training time, we're going to pick a set of observations. In this case, it samples from the signed distance function of one of the objects. And we're just going to train this meta signed distance function with the set of observations as if we were just training a signed distance function. So like deep SDF. But the only difference is we're going to do that for only 5 gradient descent steps. So using these observations, we're going to specialize our meta SDF with 5 gradient descent steps. And that gives us a specialized signed distance function. Now we're going to make a set of final predictions on points from our object. And now what do we backpropagate our loss into? We backpropagate through the gradient descent optimization algorithm, because gradient descent turns out to be differentiable just fine, into the weights of the meta signed distance function. So we are literally optimizing our the initialization such that we can quickly specialize it to any other specialized signed distance function. Okay, and this is cool because at test time, this allows you to reconstruct an object in only 5 gradient descent steps, which takes on the order of 400 milliseconds now. So these are 5 gradient descent steps. And we went from the initialization, which was just this little blob, to this full signed distance function. So the red layers, these are the level sets. And you can see that the reconstruction looks quite reasonable. And this takes on the order of 400 milliseconds only. Cool. And now you can ask, how does this compare to deep SDF? It performs approximately on par. So the reconstructions, both the qualitatively and quantitatively, performs approximately on par, but it is 1 order of magnitude faster. And we do quite slightly better on objects that are out of distribution, like very weird airplanes, for instance. We also compare this to an architecture with a point net encoder that takes as input only points from the level set. This is interesting because it's actually related to what we did in the very beginning with Siren, because this is implicitly solving the iconal equation. So we only go from surface point observations to the full side distance function. And this is related to occupancy networks as well, which had a similar experiment in the paper. And we use here a point net encoder. So it's like a permutation invariant set encoder. It takes as input the surface points and predicts the side distance function. And here we do quite a bit better. But again, qualitatively on common airplanes or common shapes, it performs approximately on par, but we do quite a bit better on airplanes that are out of distribution or shapes that are out of distribution. So another interesting thing that you can do is after you reconstructed a variety of side distance functions, in this case, it's 2D side distance functions of the MNIST data set. So the contour of the digit, that's 0 level set. You can take the parameters of the respective neural networks and do a t-SNE embedding of them. And maybe unsurprisingly, but nevertheless cool, I think, you can find that the parameters of the network now encode information about the digit class. So this is exactly a 2D t-SNE embedding of specialized network parameters for the 10 different MNIST digits. And you can see, although they're not perfectly linearly separable, clearly these parameters carry information about the underlying digit class. So this was this project was only concerned in how can we learn a prior over these implicit neural representations and how can we do test time inference fast. So we already hinted at this in this little MNIST t-SNE plot, but now you can ask, like, we have this neural scene representation now. We have some representation of the underlying 3D scene. Is this useful for anything? Are the features that we learned useful for any kind of downstream task? And this is work with Amit Palkoli, who's going to start a PhD at Berkeley momentarily. So let's go back to scene representation networks, and let's think about the last and final step of the rendering pipeline, which was we had identified the intersections with scene geometry, and now we just sampled our scene representation network a final time. We got a feature vector, we translated it into a color. Now, there's an insight, which is that the semantic class is a local scene property. So if you pick some hierarchy or like some granularity of semantic classification, then given that hierarchy, every XYZ coordinate has a unique semantic class. So for instance, this feature vector here of the point on this red square should tell you that this point belongs to a red square. So now how could we exploit this? We could of course just like tag on the segmentation classifier on top of the feature vector and then collect a huge data set of like color, camera, like RGB image, camera intrinsics, camera pose, and segmentation image, or like segmentation mask. But then we would have to collect this huge data set, and it's not great. So we're going to look at this interpolation example again, this time with cars. And I ask you, in this example here, take a look at the wheels of the sports car. And notice that the wheels of the sports car smoothly interpolate to the wheels of the limousine, although these two objects are very different. And we've seen this before as well with occupancy networks and with side distance deep SDF as well, that these implicit representations already clearly carry some information about the semantic class of these different points. So maybe we can get away with a semi-supervised approach. How is that going to look like? We're just going to train our scene representation network end-to-end without any semantic supervision at all. So exactly what we did before in scene representation networks. And then we're going to have a second step where we freeze all the weights of the hypernetwork and of the MLP that translates feature vectors to colors. And we're just going to have a linear classifier, takes as input the feature vector and maps it to the class probabilities. And this classifier is linear. And so it can't overfit much. So we can train this with much fewer observations. And at test time, this allows you to actually then go from only a single RGB image to both the 3D reconstruction of the object plus a continuous 3D semantic classification of the object. For now, we're still dealing with ShapeNet cars and chairs. So let's look at a few examples. So we pre-train on the whole chairs data set in ShapeNet, but we fine-tune the semantic classifier on only 30 semantic masks. So we're going to pick 10 chairs, and for each of the 10 chairs, we have 3 semantic segmentation masks. And these are all test reconstructions. And so on the top row, you can see the semantic segmentation of the chairs. In the bottom row, you can see the ground truth, and then in between, there's 2 baselines. Tachenko et al. Again, and a UNet that is trained on the output of the scene representation network with these 30 images. And maybe unsurprisingly, if you train a ConvNet with 30 images, there's not much you can do. But with the proposed approach, you can do quite well. So of course, this is a very simple example for now. But I think it's very cool that this works. And in fact, it also works. We've recently tried with only a single semantic label mask. And that's cool because you can actually take as your only semantic observation a shot of a chair where the hind legs are occluded. So you only see the front legs. You never see the backrest of the chair either. But from that single labeled example, you can actually correctly classify both the hind legs and the back of the backrest and so on. Cool. So this was the last project. Now we're going to recap. This didn't play again. So the first project we talked about, no, this is not cool. Let's try that again. There we go. So the first project we talked about, that was Siren. And the key idea here was we want to represent complex signals of, for instance, like this room scale scene. And we want to show that we can use these implicit neural representations also for physical signals. The second project was how can we leverage implicit neural representations to do few shot reconstructions of 3D scenes, including appearance and geometry. Then we looked at how can we infer these implicit neural representations fast with gradient-based meta-learning. And lastly, we showed that, albeit in a simple example, the features we learn in this process already carry information about a useful downstream task, which was semantic classification, segmentation. So now, what's next? So we already talked about one avenue of future work, which is this apparent conflict between generalization and photorealism. And I think one challenge we have to overcome to get there is this question of compositionality. So if you look at this scene of an airplane, you obviously realize that all these chairs are instances of the same chair class. You do not, So if we wanted to ever have a hope of reconstructing this, this scene from only the single observation, we will probably have to do the same. And that's what I call compositionality. So then another challenge is, which I'm excited about, is dynamics. So if you watch all these videos here of this gentleman bouncing balls around, you can understand a lot about each of these balls. You can understand that the ball at the top left corner is much more bouncy than the other ones. You can understand that the basketball in the second column on the top desperately needs to be inflated with more air, and so on. So I think that if we had that, in principle, it should be feasible to learn something about Newtonian mechanics just from watching these kinds of videos. So time and dynamics is a very interesting aspect for implicit neural representations. And then this is maybe my favorite example. So this is this very shiny car. It's not my car. You can see it's polished and nice and so on. The reason why I have this example is because the car is so polished that you can see the person who takes the video reflected in the car. You can see right here, the video is going to freeze in a moment with a better shot where you can see the person. So you can see the gentleman walking around. There we go. So if you look at this frame, what your brain isn't thinking, I assume, is that this is a tiny misshaped human that is approximately 2 meters away from the camera, right? What you are definitely thinking is, oh, this is the reflection of this person. And from looking at this very distorted reflection, you can infer something about the underlying 3D scene here. You can understand how this gentleman is approximately standing. You see that he has a gimbal in his hand and so on. And I think eventually we want to get to reconstructing scenes like this also with implicit or with neural scene representations in general. And for that, we're going to have to model light transport. So now there's an endless thing of things we can model, of course. And one question is for sure, for which of these aspects should we have inductive biases? Which of these should we model explicitly, and which of these we should learn? And that's an interesting discussion all by itself. But I think in the end, what I'm very interested in is I really want to work on neural scene representations that are as rich as the representations that we humans have. Because I think this is very impressive. If you think about you're sitting in your room right now, watching this video, if you were to close your eyes and think about what you know about the room around you, the kind of information you save is extremely, extremely rich. You know about geometry, you know something about lighting, you know something about materials, semantic information, affordance, path planning. You have a representation of this room that we don't know how precise, but definitely has a lot of information about this environment you're sitting in. And I think, or I hope that eventually we can get to something like that also in computer science. And I want to acknowledge all my collaborators. In the first row, that's the people that worked with me on Siren and on Meta SDF. And this was truly a group effort. So this was like quite an ambitious project. So make sure to check them out. All their websites are linked on each of the project pages. And then also Amit, Michael, whom you probably all know, and Richard and Noah, also amazing collaborators. And that's the end of my talk. Thank you so much for your attention and for having me.
Super. Thank you very much. Fantastic talk. Let me quickly stop the recording.